Hi everyone. Let's go ahead and get started. So, last time we introduced something called cosets. So let me just remind you what those were, because that's going to come up a lot today. So, if G is a group, Bean. If G is a group and H is a subset of G, then this is called, and let's see, we also have an element A in G. Then AH is the set of all A's times H's, such that H is an element of H. This is called the left coset of A in the left coset of H in G containing A. And last time we started proving some properties of cosets, so let's continue with that. So we had properties of cosets, and we already proved that the first property, which is that an element A is contained in AH. So this is when H is a subgroup. Of G. So we already showed that A is in the coset AH, and that's because the identity element is in H, and so A times the identity is in AH. And I'm going to give you three more properties. So the second one is that AH is equal to H if and only if A is contained in H. The second one, or the third one, is that either AH is equal to BH for some other B in G, or they are disjoint. Bean. And the last one says that the number of elements contained in AH is equal to the number of elements in BH for all A, B, in G. So I'm going to give you a few minutes to think about these properties and think about how to prove them, and then we can discuss the proofs together after that. Bean. Bruh, you're being like terrible. Yeah. For the last one. I guess for the last one, assume that H is a finite subset of G. I don't think so. Yeah. So, like, let's go back to this example. So only the first one had the identity in it, yeah. Mm-hmm. H is, yeah, H is the same group. Okay, should we go ahead and prove these? So I'm just gonna scoot these down to make room. So for this one, we have two directions. So let's assume that AH is equal to H. Well, by the first property, we have that A is contained in AH, and this is equal to H. So we can conclude that A is contained in H. So that shows that if AH is equal to H, then we have that A is in H, and the reverse direction. So if A is an element of H, then it is clear that AH is a subset of H because H is a subgroup, so it's closed under multiplication. And then for the other inclusion, why is H a subset of AH? So if we have some H, some little h in capital H, then we also have A inverse H is contained in H. because you know that A is in H, and so A inverse is also in H, and so the product A inverse H is in H. And so that means that A times A inverse H is in AH. So that means that H is in AH. Okay, so that shows that then AH is equal to H in that case. So that proves the second, this number 2. Are there any questions about that? Okay, so for 3, so we have to show that, so given an A and a B, we want to show that either AH is equal to BH or they are disjoint. So, so let's suppose that they're not, so let's suppose they are not disjoint. So then it suffices to show that then AH is equal to BH to prove this statement. So let's suppose that there is an X that's in their intersection. So X is in AH, intersect BH. Okay, so we want to show that they're equal. So we know that there are H1 and H2 in H with X equal to AH1 because we know that X is in AH and we have that X is equal to BH2. Okay, so there exists H1 and H2 so that this holds. And then if we rearrange this first equation, we get that A is equal to X H1 inverse. And then let's substitute in for X using this equation. So then we have A is equal to BH2 H1 inverse. And so what does that mean? We have that then AH, this is equal to BH2 H1 inverse. And then by property 2, so what we're going to do, this is BH2 H1 inverse times H. So then what we're going to do is, by property 2, this property that we already proved, basically H can absorb anything that's already in H. So this is equal to BH. Okay, so we showed that if these two cosets are not disjoint, then they are in fact equal. So either they're equal or they're disjoint. And that finishes that part of the proof. Are there questions? Okay, so let's prove this last bit. And these properties are going to form basically all of the ingredients that we need to prove Lagrange's theorem, which will come next. So that's why we're doing this. So to do this, I'm going to write a correspondence or a bijection between the elements of AH and the elements of BH. Okay, so everything in AH is of the form A sub little h. So what I'm going to do is map that to the element of BH that's given by BH. Okay, and then we just have to see that this correspondence is one-to-one and onto. So let's see that this is injective. So if AH and AH prime are sent both to some B, so let's say they're sent to the same element. So let's say they're sent to the same thing in BH, so then that means that BH, which is the thing that AH is mapped to, that's mapped to the same thing as whatever AH prime is mapped to, which is BH prime. So then by cancellation, we have H equals H prime. And so that means that, in fact, we had AH is equal to AH prime. Okay, so that shows that this correspondence is injective. And then why is it surjective? If I have some element by in BH, then I claim that AY is mapped to BY, and this is clear just by the way we set up the correspondence. So since there's a bijection between the elements of AH and the elements of BH, that means that that they have the same number of elements. Okay, are there any questions? Okay, so now we are ready to state and prove the most important theorem of finite group theory. So this is called Lagrange's theorem. And this is going to generalize some results that we've seen already for cyclic groups, but more generally to any finite group. So this says that if G is a finite group, and H is a subgroup, of G, then the order of H divides the order of G. So that's the first part. So recall that we had the fundamental theorem of cyclic groups, which said that for every divisor of the order, we have exactly one subgroup. So this is sort of a generalization of that, in that we now know that the order of a subgroup must divide the order of the group, but we aren't guaranteed that there is a subgroup of every possible order or that there is just one subgroup of a given order. We just know that it has to divide. Okay, the second part of this is that the number of left cosets of H in G is the order of G divided by the order of H. Okay, so that's the theorem. And basically, we've already shown all the ingredients that we need to prove this theorem. The basic idea is that the cosets of H in G partition G, and we are able to determine their size. So let's prove this. So we show the left cosets of H partition. So this, we have to think back to just the first couple of days of the semester when we talked about partitions. So we need to show first that the cosets cover G, so cosets, i.e. that every element of G is in some coset. 2, that they're disjoint. And 3, we also, in order to draw this conclusion about the size, or about the order of H dividing G, we also want to show that all cosets have the same size, which we sort of have already shown. So all cosets have. Okay, so why do the cosets cover G? So let's let A1H up to A sub R H denote the distinct left cosets of H in G. So let me just go back to the example from last time quickly. So we had this example in Z mod 9. So we saw, a priori, there's 9 elements of this group. So we have 9 cosets, but they did end up producing duplicates. So in our setup, what we want is just the distinct cosets. So that would correspond to these 3 sets. Okay, so going back to the proof. So we're going to let A1 up to AR H denote the distinct left cosets of H in G. And then given an arbitrary A in G, we need to show that this A is contained in one of these cosets. So consider the coset AH. It is among the ones that we've listed because this is supposed to be a complete list of the cosets. So we have AH is equal to A sub IH for some I. And then we know by the lemma that we had just earlier that A is contained in AH, which is equal to A sub IH. So we can conclude that every element of G is in some A sub IH. Okay, is that clear why the cosets cover G? Okay. So by the lemma, we have that so any cosets either are they are equal or they are disjoint. So since this is a list of distinct cosets, we have that the A1 up to the A1H up to ARH are pairwise disjoint, meaning if I compare any 2 of them, they do not overlap in any elements. So that means that we can write the order of G as the sum of the orders of the A sub I H's. But then we also showed that all cosets contain the same number of elements. That was like part 3 of our, or part 4, this part. So that means that we actually have that the order of G is equal to the number of cosets that we have, which is R, times the size of the subgroup H, because the size of A sub I H is going to be equal to the size of H. And so this tells us both, so from this we can conclude that the order of H divides the order of G, since R is an integer, and also that the number of cosets is equal to the size of G divided by the size of H. And that completes the proof. Are there any questions? Yeah.
The number said that any two, like AH and BH are either equal or disjoint. Why are you only assuming that they're all disjoint here? Why don't you assume that they are simultaneous equal?
Because we set this up just asking for a list of the distinct cosets. So yeah. Yeah.
Why do we know that size of AI is
Because of part 4 of this. So we know that if we compare the size of any two cosets, that they're the same. Yeah. 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 Bean. So yeah, we proved everything that we proved for left cosets will also be true for right. Other questions? Okay, so for, let's do an example, or see if we can think of examples. So for cyclic groups, we had that, so if G is cyclic, we have, and N divides the order of G, then we know that there is a unique subgroup H with the order of H equal to N. So let's see that this can fail for arbitrary groups. So let's come up with an example where of an N that divides the order of some group, and there's no subgroup of order N. And let's come up with an example where N divides the order of the group, but there's multiple subgroups. Of order N. Can anyone think of an example satisfying either of these? Maybe I'll give you a couple of minutes to think about this, and then we can talk about the examples. Hey, Bean, what you doing? What you up to? You're like hungry? Okay, did you all come up with examples that satisfy either of these? So did anyone find an N and a G with no subgroup of order N? Yeah.
So for G, I have 1, 8, and
You had, sorry, what?
B. E, 8, and B as the elements, where
Wait, E? E8 and B?
8, 8.
Oh, E. Okay, yeah, yeah. E, A, and B. Okay.
And then A squared is equal to B, B squared is equal to A, and AB is equal to A and B are the inverses of each other.
Okay, wait, so,
So the multiplication table I can do is, if you have,
okay, I'm with you. So, but this is a group of order 3.
yeah, but then if n is 2, then we have, oh wait.
But N doesn't divide the, yeah. Okay, other examples? Examples of this other type? Yeah.
So if we let G be the quaternions,
Okay, yeah, this isn't an example that like we've talked about yet, but you may have seen it in other places.
where is A and 4 has A and we have like these subgroups?
Yeah, okay, so the order of G is there's 8 of these. And do all of the subgroups have order 2? Oh, but okay, so all subgroups are either order 2 or order 4? Okay. The example that I thought of, we haven't really discussed this yet, but we will soon. So if you take Z mod 2 and then you can raise it to a power. So this is just tuples, so A, B, such that A and B are both in Z mod 2. So this is a class of examples that we haven't talked about yet, but we will get to this sometime next week. But every subgroup here has order 2. So in particular, it has 3 subgroups of order 2 and no subgroups of any other orders. So there's 4 elements in this total. So 4 is a divisor that has no subgroups. I didn't do this, but you could probably find a U group that is isomorphic to this. I just don't remember which U group it is. Okay, so let's see some consequences of Lagrange's theorem. So the first couple will be just easy corollaries. So the first thing, and this is just a piece of vocabulary that comes up sometimes. So the index of a subgroup H in G is the number of distinct left cosets. And this is a useful idea because often your subgroup H and your group G will be infinite, but the index will be a finite number. So then you are able to sort of talk about the index, which is a finite quantity, bean. And this is denoted like this, so G colon H. And by Lagrange's theorem, we have when G is finite, we automatically have that G colon H, that the index is equal to the order of G over the order of H. Okay, so that's one corollary. As a second corollary, we have that the order of any element A in G divides the order of the group. So why is that? Yeah. So what is H here? Sorry, what is the subgroup H for this? But then what is, so how does that relate to the order of A? Other ideas? Yeah. Yeah, so we know that the order of an element is equal to the order of the subgroup generated by that element, and we know by Lagrange's theorem that this divides the order of G. So taking H to be equal to the subgroup generated by A. Okay, so then as a corollary of this corollary, we have that, so if G is a finite group, and this should have also been finite here, this G, which I guess is clear whenever we're talking about the order of G as a finite number, but okay, so if G is a finite group, and A is in G, then A raised to the order of G power is equal to the identity. And why is this? We know that the order of A divides G, so that means that, so let's say the order of A is equal to K, and then G over K, let's say this is N. So then the A raised to the order of G is equal to A to the Kn, which is A to the K to the N, and A to the K is just the identity. Okay, so we have this, this equality. So on problem set 4, you had a problem where in the hypotheses I included that every element of your group satisfied x to the 77 is the identity. So do you guys remember that? So this was like actually unnecessary to include because that's like automatically true about any group, but for the problem set, I had to include it because you all didn't have this like fact yet. So that's why that hypothesis was there. Okay, so let's see one other corollary. There's two more that I wanted to talk about, but I'll do one of them on Monday. So here's another corollary. And this one is maybe less obvious. So this one is called Fermat's little theorem. And it says the following. So for any integer a and a prime number p, we have the following. A to the p mod p is equal to a mod p. Okay, so we're going to prove this using Lagrange's theorem. So first, I'm going to start with the case where I have a number between 1 and p minus 1 and prove it just in this case. So we'll just show r to the p is equal r to the p mod p is equal to r mod p, just when r is a number between 1 and p minus 1. So notice that this is equal to the u group u of p, so all of the numbers less than p that are relatively prime to p. So by the previous corollary, we have that if we raise any element of up to the size of up, then we get the identity. So that means that r to the p minus 1 mod p is equal to 1 mod p. So then I'm just going to multiply both sides of this equation by r, and I have r to the p mod p is equal to r mod p, as desired. Okay, so now for the general case. So I'll let, are there questions about just the case when r is between 1 and p minus 1? Yeah. Yeah, okay, yeah. So this was, this step was because the order of u of p is p minus 1. Okay, so then for the general case, I'll let a be any integer. And then by the division algorithm, I can write a is equal to p times some number m plus some remainder r. Okay, so if r is equal to 0, what am I looking at? So I have a to the p mod p, which is, so just substituting in with my division algorithm, this is pm to the p mod p, which is equal to 0 because everything here is a multiple of p. And 0 is also equal to a mod p because I'm in the case r equals 0. So in this case, it works. And then otherwise, r is between 1 and p minus 1. So we already proved that it works for that case, so let's see what happens. We take a to the p mod p, and this is equal to pm plus r to the p mod p. And then this is just equal to r to the p mod p. Why is that? Because if I were to take this product, every term that has a p in it will be killed by modding by p. So all of those will be 0. And so the only term that survives is this r to the p. Okay, so this is r to the p, and then by the first part, this is equal to r mod p. So this is by the first part. And r mod p is equal to a mod p. Because this is our expression for a. So if we mod by p, then we're just left with r. And that finishes the proof of that. Okay, so we will on Monday have one more application of Lagrange's theorem, and I hope you all have a good weekend. Bean. Yeah, so the elements are like 0, 0, 1, 0, 0, 1, and 1, 1 as the elements. So, like, what's the subgroup generated by this?
What's the operation, or is it still?
So it's addition. Yeah, so
So
if I
is it
mod
element-wise?
2. Yeah, sorry, you do it, element-wise. So then this would be like, so 1, 0,
It'd be like zeros.
yeah. And same thing here, if you like add it to itself, you get 0.
So both of those have order 2.
Yeah,
And you
then,
can do the same with these two, right? 1, 1 plus 1, 1 is 0, 0.
yeah.
Oh.
So every element has order 2.
Weird to think about doing it element-wise. Okay, that makes
Yeah.
some sense now. The other question I had, right. I think at the beginning of class, I kind of got cosets and subgroups mixed up. So a coset isn't always a subgroup, right? Because you can have cosets that don't have the identity. Okay.
Yeah, so I think that the example that we did with Z9 is a good one to keep in mind. That like it breaks down into,
Oh, like 0 plus h, 1 plus h, etc.
yeah, so like I forget what our h, oh yeah, h was like 0, 3, 6. That the cosets are just, so if this is h, then these are all of the distinct cosets.
Yeah.
So like, yeah, like these aren't
Don't have the
subgroups.
identity.
Yeah.
Okay.
Yeah, so cosets are usually not subgroups.
Okay. Also one random thing, why is Lagrange's theorem considered the most important? Like, it's really cool, but...
I don't know.
Okay.
I guess like it will continue to pop up over and over again because now like anytime you start to analyze a group, you're like, okay, how many elements does it have in certain orders, and you know that the only options are numbers that divide the order of the group. So it is like very useful. Yeah, I don't know. I think it's just like funny when
It's
folks
so
say something
exaggerated.
like
It's like
this is the most important theorem. It's like how can you say what is the most important theorem? But whatever.
Objectively, it's
Yeah.